Hello students, we are going to start the new chapter on principal stresses and principal strain. To understand the principal stresses, let's first understand the plane on which they act. These planes are called as principal planes in general. So the definition goes by that at any point in a strained material, there are three planes mutually perpendicular to each other which carry direct stress or the normal stress only and no shear stress. These are called as the principal planes. And the stress which acts on these planes are called principal stresses. So mind it, there are always at any point in the strained material you can find the three planes which are mutually perpendicular, and on these planes there will not be any shear stress present and only normal stresses will be present, and the value of these normal stresses that you find on these planes will be termed as principal stresses, and these planes will be called as principal planes. Now because there are three different values of stresses, so one of these may be the maximum amongst these and the other one may be the least value amongst these. So in some cases you may also find that all these three normal stresses are equal in magnitude. Now once we understand that what is the principal plane and what is the principal stress, we will work out the value of these for different cases of loading. Before going further, let's understand the sign convention. So what you see here is a coordinate axis of xyz. The origin is shown to you. Now within the strained material you are seeing this is small cube like portion. Now on the plane, the stresses which are acting perpendicular to the different planes are the normal stresses. So those are shown here in the red. So here there is a sigma x, sigma y, sigma z, and you are well aware of them. These are the normal stresses, and the convention goes by that in the direction that they act, they will get the suffix of that. So sigma x is the stress in the x direction, sigma y is the stress, normal stress in y direction, and sigma z is the normal stress in z direction. Now comes the shear stresses. Shear stresses are the stresses which acts parallel to the planes. So there are three planes, of course. There is the xy plane, yz plane, and zx plane. Now the stresses which are acting in the plane xy are basically tau xy and tau yx, which you can see over here. This is tau xy and these are tau yx. And for the sign convention we take in such a manner, like for if we take the case of tau xy, it is the shear stress value in the direction perpendicular to x and in the direction of y. So tau xy is perpendicular to the x marked here and is in the direction of y. Similarly, tau yx here is perpendicular to the y in the direction of x, but these both are acting in the xy plane. So these are a pair of or the complementary shear stresses acting in the xy plane. Similarly, you have the yz plane. So you have the stress tau yz and tau zy, which is the complementary shear stresses of each other. So tau yz is the shear stress acting perpendicular to the y direction in the z direction. So this is tau yz, and tau zy is the shear stress acting in the direction perpendicular to the z and in the y direction. So that is tau zy. So in this way you can also identify the value of tau zx and tau xz, and this is the way we are going to mark these stresses. Now let's calculate the value of principal stresses and identify the location of the principal plane, starting with the most simple case of the stress induced in only one direction. Okay, so let's first start with this case. So there is a load P of magnitude, tensile in nature, acting in the direction x. Okay, so this is the load P which is acting in the direction of x. So this is some simple rectangular object on which this load is being acted upon. This is a bar, and we need to find the stress components along and across an inclined plane AB. So this is my inclined plane AB, on which I need to find the stresses perpendicular to it and parallel to it. So the perpendicular stresses to the normal to AB will be the normal stresses, and the stresses which will act parallel to this will be the shear stresses acting on this plane. Obviously, you know the value of stress on the plane AC, which will be simply load divided by the area of this bar, cross section area of the bar. So if A is the area of cross section of the normal section AC, we can find the area of cross section of section AB by simply the simple trigonometry, that is AB will be equal to A sec theta. Okay, because AB cos theta will be equal to AC, and the thickness remains same for both of these components. So therefore the area of this section AB will be A sec theta. Okay, now stresses which are acting normal to AB, which we term as sigma theta, will be given by force normal to the AB, which is Pn, P normal, and the area of cross section of the AB. Now force normal to the AB, Pn, this value we can find by resolving the force P in the direction of Pn. So here I have just moved the load P backward, so it coincides with the origin of the Pn, and we see that it is making angle theta with the Pn. So the component of load P in the direction of Pn will be P cos theta. So that's why force normal to AB will be P cos theta, that will be equal to Pn, and the area of cross section of AB will be equal to A sec theta, as we have just calculated. So this gives us the value of sigma theta, or the stress perpendicular to AB, as P by A cos square theta. Now P by A is nothing but the value of stress in x direction, that is sigma x. So I represent it with the sigma x, and sigma theta will be computed as sigma theta equal to sigma x cos square theta. Now comes the case of stress tangential to AB. The tangential stresses are the shear stresses, so I represent it by the symbol tau theta, shear stress acting at angle theta. So that will be equal to the force parallel to AB, that is your PT. So what will be the value of force PT? It will be the sine component of the load P, so that is P sine theta. So P sine theta will be the force normal to parallel to the AB, that is PT, and the area of cross section of AB will be A sec theta. So that gives me stress tangential to AB as P by A sine theta cos theta. For P by A, I am substituting again here as sigma x. I am multiplying and dividing both by 2 here, so that I can represent 2 sine theta cos theta as sine 2 theta. So this is going to be the value of tau theta, which is sigma x by 2 sine 2 theta. So in this way, by resolving the forces perpendicular and parallel to the plane where we want to find the value of normal and tangential stress, we can calculate the value of stresses acting perpendicular and tangential to the plane in question. Now sigma theta value here, you can see here this value will reach maximum when theta is equal to 0 degree, because cos theta is maximum at theta equal to 0. So sigma x cos square theta will be maximum when theta equal to 0. What is the meaning of theta equal to 0? That means this plane AB will coincide with AC. So obviously we know that the maximum value of stress will be when the plane is perpendicular to the applied load. So that will give you the maximum value of normal stresses. And then what will be the maximum value of the normal stress? That will, sigma theta will be equal to sigma x, right? Now the tau theta, which is the tangential stress, that will be maximum by this formula when theta is equal to 45 degree. So when theta is equal to 45, sine 2 theta will be sine 90, which will be 1, and the maximum value that you will compute for the shear stress will be sigma x by 2, that is half of the normal stresses acting on the plane. Okay, so tau theta will be equal to sigma x by 2. So that is the maximum value of shear stress. You see here you must have noticed that we are applying the normal load, but the plane which are inclined to the application of load will carry both normal and shear stresses, and these shear stresses will be maximum when the angle between the applied load and that particular plane is 45 degree. So I was at these planes, the shear stresses will be maximum, and their maximum magnitude will be equal to sigma x by 2, or half of the applied normal stress. The resultant stress of the resultant stress sigma r, because of the sigma theta and tau theta, can be determined by simply taking the under root of these square of the under root of these quantities and summing them. So sigma r will be equal to under root of sigma theta square plus tau theta square, because sigma theta and tau theta are perpendicular to each other. So you can compute their value by substituting the value here of sigma theta and tau theta respectively, and you can obtain the value of the resultant stress as sigma x cos of theta. Now let's talk about the stress on an inclined plane subjected to two mutually perpendicular stresses. So in this case, instead of one normal load, there are two normal loads which are acting in the both the direction, in x and y direction, which are shown here with the px and py. Okay, so you have a block here ABCD. This is the kind of a bar or a rod, and there is a load of magnitude px applied in the direction x. There is a load of magnitude py applied in the direction y, and the length of the rod is L, which is given here. Okay, the length of the rod is L, the width of the rod is B, and the thickness of this rod is T, which is in the plane of the paper, okay, or the plane of the screen that you are watching. So length, width and thickness is L, B and T respectively, and we need to determine the normal stress and tangential stress at an angle theta to the direction to the, let's say, the plane BC. So we need to determine the stress value on the plane BD, which is at angle theta to the BC. So let's draw this triangular portion ABD separately, and let's show the forces which are acting on it. So the forces which are acting are Px and Py, and I have drawn them over here again. This is the my figure of triangle ABD, and this is the force Px, okay, and this is the load Py which is acting here, and I will transfer them back, these vectors for forces, and so that they will meet at this point here, and the normal force perpendicular to BD is called as Pn, and the tangential force is called as Pt. Okay, and you can see these angles also. You can easily see that if angle is this angle is theta, obviously this will also be theta. So this will be 90 minus theta. So obviously this angle will be theta here. Okay. So after drawing this figure, I am now ready to resolve the forces so that I can determine the value of Pn and Pt. So let's start first with the case Pn. So the load normal to the plane BD. So the value of Pn will be obtained by resolving the forces Px and Py in the direction of Pn. So if you resolve the force Px here, it will be having magnitude of Px cos of theta in the direction of Pn. Of course, it is opposite to that. So Pn will be equal to Px cos theta, and the component of Py in the direction of Pn or normal to BD will be Py sin theta. So Px cos theta plus Py sin theta will be the net sum, which will be equal to Pn. Similarly, for finding the force tangential to the BD, which is we called as Pt, we can resolve the forces in the direction of BD. So if you do this, there will be a force Px will be resolved as Px sin theta, and Py will be resolved as Py cos theta, but they are acting in the opposite direction, so there will be a negative sign coming between them. So here we have values Px sin theta minus Py cos theta as equation 2, which is will equal to Pt. Now let's substitute the value of the forces in terms of the stresses to which they correspond. So let's do this exercise. So load Px will be equal to simply the stress acting in the direction x, normal stress sigma x, multiplied by the area on which it is acting. So Px will be equal to sigma x into B into T. You see the T is in the plane of the screen, that is inside. B is the width of this rod. So B into T will be the cross section area on which the load Px is acting. So therefore the stress acting in the direction x multiplied by width into thickness will give the value of load Px. Similarly, you can find the value of load Py, which will be equal to stress in the y direction multiplied by the length into thickness of the rod. So Py will be equal to sigma y into L into T. Now comes the Pn, load acting perpendicular to the BD. So if I call the stress perpendicular to BD as sigma theta, so the value of sigma theta multiplied by the cross section area on which it is acting is BD multiplied by the thickness of the rod. So BD into T will be the area on which it is acting. So the Pn will be equal to sigma theta into BD into T. The BD can be expressed in terms of AD by using the triangle ABD, because BD cos theta will be equal to AD. So therefore BD will be equal to AD by cos theta. Okay. So we substituted it over here in this equation, and as AD is nothing but your width B, so you substitute here sigma theta dot B by cos theta into T, that equals to your Pn. Similarly, you can express the load Pt in terms of the tangential component of stress, that is tau theta, and as it acts again on the same area BD into T, so I will simply summarize it as tau theta into By cos theta into T. Now we will substitute the value of these loads Px, Py, Pn and Pt back into the equation 1 here. So you will get this expression as shown over here. If you multiply, because you are getting on the left hand side By cos theta into T, so if you multiply to the right side the term cos theta divided by Bt, you will get the sigma theta as sigma theta equal to sigma x cos square theta plus sigma y L by B sin theta into cos theta after simplification. Now sigma theta, this expression can be further simplified by, this expression can be further simplified by substituting tan theta for the place of L by B. If you can see here, the tangent of angle theta here, tangent of angle theta will be equal to length divided by width. Okay, so therefore for tan theta we will substitute L by B. For L by B we will substitute tan theta. So if you do this after simplification, you will obtain the value of sigma theta as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos of 2 theta. This is simple some mathematical manipulation which we performed here for substituting cos square theta as 1 plus cos 2 theta by 2 and sin square theta as 1 minus cos 2 theta by 2. Similarly, we can do the substitution of the values of Px, Py, Pn, Pt in the equation 2 in order to get the value of tau theta, and after doing small mathematical manipulation by substituting L by equal to tan theta, you can get that value of tau theta as sigma x minus sigma y by 2 into sin 2 theta. These are two very important expressions which we'll use frequently in order to solve the numericals on the part. Now this tau theta will be maximum when theta will be equal to 45 degree or 135 degree, because this is tau theta is equal to sigma x minus sigma y by 2 into sin 2 theta, and sin 2 theta will be maximum when theta will be 45 degree, and the maximum value will be sigma x minus sigma y divided by 2. Okay, and the resultant stress on the inclined plane will be simply obtained by taking the squaring of this quantity of sigma theta and tau theta and adding them and taking the under root of it. The angle on which this resultant stress will act will be given by tan phi equal to tau theta by sigma theta. Now in case you see here both the stresses sigma x and sigma y are tensile in nature, but if one of these are compressive in nature, you need to change these formula by substituting that particular term with a negative sign. So tensile stress positive in our sign convention, compressive stresses are negative. So suppose if either sigma y is so let's say the compressive in nature, so formula from equation 4 will get changed. It will be sigma x plus sigma y by 2 into sine 2 theta. Similarly, the formula of here will also change. There will be negative sign coming over here and a positive sign coming over here accordingly, if in case the sigma y is compressive and sigma x is tensile in nature. So that we need to remember. Now let's do some numericals on this. Let's start with a very simple numerical. This is our first numerical. We have been given a circular bar and it is subjected to the axial load of 180 kilonewton. So the load value is given to us, and the maximum intensity of shear stress on oblique plane is limited to 65 megapascal, and you need to find the diameter of the bar. You see here the value of the maximum stress, shear stress that can be applied on the object is given to you. You see, when we have the ductile material, they will always fail because of the shear stresses, not because of the normal stresses. You have just seen that though you applied the normal load only, there will be a planes, inclined planes, on which there are shear stresses acting. And in case of ductile material, the primary reason for the failure is shear stress. It's not the normal stress. So therefore, it is like aluminum or mild steel or some other material. For these materials, the theory of failures that we use is called the maximum shear stress theory, and we will talk about it in detail later maybe, but right now it is important for us to understand that the maximum intensity of shear stress is limited for certain materials which are ductile materials. So let us say that this bar is made up of a ductile material and the maximum value for this is given as 65 megapascal. You need to design this bar, you need to find the diameter of the bar. So we know that the area of the bar is given by pi d square by 4. Okay, and the direct stresses which act sigma x, okay, will be given by load divided by area. So load is given to you as 180 kilonewton, so it is 180 into 10 to the power 3 divided by area of cross section is pi d square by 4. So that gives you this expression for the direct stress. Now the maximum shear stress on an inclined plane in case of a uniaxial loading is given by sigma x by 2. We have just calculated that the maximum shear stress value will be given by sigma x by 2. In case there are biaxial stresses, what is the formula? The formula is sigma x minus sigma y by 2, right? Because there is no sigma y here, so only sigma x is acting, so maximum shear stress will be sigma x by 2. So you substitute the maximum shear stress value that is permitted here as 65 megapascal. You substitute for the sigma x here from the this expression here, and you calculate the value of diameter as 0.042 meter or 4.2 centimeter for this rod. Now let's look at the another numerical. Here you have a prismatic bar which is carrying the axial tensile stress sigma x, okay, and on the oblique section the value of the normal stress sigma theta is given as 90 megapascal and the value of shear stress tau theta is given as 30 megapascal. What you need to do is you need to find the value of sigma x. So what is sigma x here that you don't know, and the angle at which this plane is inclined, theta, or the slope of this oblique plane you need to find. So these are the two things that are asked to you. So this is a kind of a reverse question. Here the value of the stresses on the planes are given, oblique plane is given, and you need to find the stress acting on the component. Let's see, take the case, let's see that this rod is having the length L and width B and the thickness T and so on. So what we do, we will resolve the forces in the vertical and the horizontal direction of AB. So you see here we have the first force that is acting here, the normal force perpendicular to the AB will be shear, the value of stress, normal stress sigma theta, multiplied by the cross section area on which it is acting. So the cross section area is AB into the depth of this object, that is T. So sigma theta dot T dot AB will be the amount of force acting perpendicular to AB. Now this is equal to how much? So for this we need to resolve the force acting because of the sigma x here. So that will be sigma x, and the component of it that will be acting in the direction perpendicular to AB will be cos of 90 minus theta. You can see from this figure that will be cos of 90 minus theta, and the area on which it is acting is again same, AB into T. So this AB into T will get cancelled out here. Okay, so what you will be left is sigma theta is equal to sigma x sine of theta. Similarly, you can prove that tau theta is equal to sigma x cos of theta, which you can see obviously from the figure also, that the tau theta is equal to the component of the sigma x parallel to the AB, that is sigma x into sine of theta. So sigma x into cos of theta. So tau theta will be equal to sigma x cos theta. Now we substitute the value of sigma theta and tau theta, which is given to you, that is 90 and 30. So you will get these two expressions. You can compute the value of sigma x from this as 94.868 megapascal. You can also work out the angle or the slope of this plane as tan theta equal to 90 by 30. Which I will, after taking the inverse of this quantity, tan inverse, you will get the 71 degree 36 minutes for this. You see, in most of the questions that you will encounter here, you will need to resolve the forces in order to determine the value of either the stresses acting on the inclined planes or the load values acting on the inclined planes, or you perhaps may be provided with the value of the stress or load values on the inclined plane, and you need to find what is the value of the load that is being acted on the actual component. So you can always find them out by doing this resolution of the forces. Now let's take one straightforward numerical, and in this numerical you are given the value of the stresses which are acting on the component. So there are two perpendicular stresses acting of the magnitude 10 megapascal and 2 megapascal respectively, and you need to find the stress values which are acting on a plane which is at an angle of 22.5 degree with the larger value of stress, that is 10 megapascal. This is a very straightforward numerical. You just need to define that the sigma x and sigma y are as 10 and 2, and you need to simply use the formula of sigma theta and tau theta which we have just derived. So you just write down these formulas and simply substitute the value of sigma x and sigma y and compute the value of sigma theta and tau theta. Mind it, here both the normal stresses are of the same nature. They both are tensile in nature, sigma x and sigma y. If I would say that let's say the sigma y is compressive in nature, so what you are going to do, you are going to make it sigma y equal to minus 2 meganewton per meter square, and accordingly you substitute for sigma y as minus 2 here. So all these formula will get changed. Here there will be negative time, there is a positive sign here, again there will be positive sign here, and so that you can compute the value of sigma theta and tau theta accordingly. So please do remember that whenever there is a one of the stress of opposite sign of, then you need to put a negative sign in front of the compressive stresses. There are some other numericals which are given in your book. Please do those numericals and have some practice.